In this video, we're gonna learn generating functions. Let me define the definition. The generating function for a sequence is an infinite sequence indexed from 0, A1, A0, A1, A2, etc. is this power series n from 0 to infinity an times x to the n. So if we write this, expand this without summation notation, then we have this infinite sum. So this is a power series, or a formal power series, so here formal means so unlike the power series that we learned in calculus, we don't consider the radius of convergence, we don't put x as a number, we don't consider the radius of convergence, and we don't plug in numbers or real numbers into x. So for instance, x equals 2, x equals 1, something like that. We don't worry about those things. We will consider this as a formal power series. So generating function is nothing but a way of recording a sequence. So for instance, the generating function for the sequence an equals just 1, so n from 0, 1, 2, is just 1 plus x squared plus x cubed, This is just generating function. The generating function for k choose n, so an equals k choose n, so n is again 1, 2, 3, 0, 1, 2, 3 is k choose 0, k choose 1, x, k choose 2x squared, k choose k, x to the k, k plus 1, x to the k plus 1, plus But after k plus 1 term, they are all 0. So it's equal to k choose 0, k choose 1, x up to k. This is in this case, it just becomes a polynomial. And we know from the binomial theorem that this is 1 plus x to the k. So this is a generating function for the binomial coefficient. So generating function is just a way of recording a sequence, but there is a benefit of doing this because we can consider some operations on two generating functions. So suppose we have two generating functions, an and bn. Then we can think of this as just polynomials, and we do the same operations as we do for the polynomials, like addition and multiplication. So ax plus bx, when we add two generating functions, we just add term by term. So it's an plus bn. We just collect the coefficient of x to the n and then add them. And we can multiply constant to a generating function. In that case, we just multiply that constant to each term. And here is the least trivial operation. So we multiply two generating functions, and the result is also a generating function, so we must have some coefficient times x to the n, where when we sum this for n from 0 to infinity. And the coefficient here is defined to be another sum. I goes from 0 to n, ai times b, n minus I. And these are really operations are say natural extensions of those of polynomials. Those for polynomials. We have operations in polynomials like addition, multiplication, they're exactly the same. So when we multiply, so for instance, when we multiply two polynomials, say 1 plus something like this, 1 plus 3x plus 2x cubed, suppose we have a polynomial like this. When we multiply these two, we choose one term in each factor and then multiply them. And this will give us one term here, 2 times x times 2x cubed. And then you take another way of multiplying them, x squared plus 3x, and then you consider all of this. Here is multiplication, and then that will be the result. And for polynomial it's the same. So a0, for power series generating functions. So when we multiply two generating functions, we take one term. So here we take one term, and here we take another term, and then we multiply them. And then the result is so we can actually see this by writing this as follows. So here we can choose any term, so it can be ai x to the I. Here we choose any term and say bj x to the j. Here of course I and j can be any number, non-negative integer. Then this means I is from 0 to infinity, j is from 0 to infinity, ai xi bj xj. Okay, and then we can multiply the two, ai bj x to the I plus j. Now we let I plus j equals n. In other words, j is n minus I. So here, and we collect them from I for n. So x to the n, and if this I plus j equals n, then I must be from 0 to n. Once n is fixed, so I is from 0 to n, ai, and because j is n minus I, is be n minus I, something like that. In other words, if we take in order to get x to the n, if we take ai here, we must we have chosen x to the I, and in order to get x to the n, we must select the term with x to the n minus I, because we want to get x to the n. So that's how we multiply two generating functions. So now we know how to multiply two generating functions. Now sometimes we have a special situation where we multiply two generating functions and suppose we get just one. If this happens, then we say that we write B is the inverse of A, and we write this as A of X inverse, or 1 over AX. This is a notation for the inverse. So B of X is the multiplicative inverse, just simply inverse of AX. So there is a very typical example for this. So let's say A of X equals 1 minus X. So polynomial is a generating function, of course. And this is 1 plus X squared plus dot dot dot. So here it means if you write this as a generating function notation, this means A0 equals 1, A1 equals minus 1, and then A2, A3, A4, they are all zeros. And here, if we write this as generating function with coefficient b sub n, then every bn equals 1. Now let's multiply these two generating functions. 1 minus x, okay, A of x, B of x, then by definition it's gonna be this. This is the definition for this. Let's compute this. So we need to compute this. Now we have two cases. If n equals 1, 0, then this is just I is from 0 to 0, so I must be 0. It's going to be A0 and then B0. And A0 equals 1. B0 is also 1, so it's 1. So the coefficient for the constant term, x to 0, is 1. And if A equals, let's say A is greater than or equal to 1, then summation I from 0 to n. This is, I is from 0 to n, but we can restrict this to the fewer terms. Like I is from 0 to 1, because if n is bigger than 1, they are all zeros. So, but now when I equals 0 is A0, Bn, plus I equals 1, A1, Bn minus 1. But we know that this is 1 times, B is always 1, and A1 is minus 1, B is always 1, so it's going to be 0. So the coefficient is An, and the coefficient is this part, is when x n equals 0, we have 1, and when n equals 1, we have, oh no, it's always 0. It's 0, 0 times x squared, all 0, so it's just 1. So we multiplied two generating functions and we obtained 1. That means one generating function is the inverse of the other. So 1 plus x squared plus is 1 minus x to the minus 1, or 1 over 1 minus x. And of course, we know that this is called a geometric series. This can be shown using only formal power series like this. Okay, generating functions are especially useful for studying partitions. So let me prove the generating function formula for the partitions. So P of n is the number of partitions of n. There is no explicit a simple explicit formula for the number of partitions, but the generating function for the partition is very simple. So, and for historical reason, generating function for partition is, we usually use variable q instead of x. So here I'm using q, but it's just like x, just variable. Then this is the infinite product. I is from 1 to infinity, 1 over 1 minus q to the I. And in other words, because each product is a geometric series, is 1 plus q to the I, q to the 2i, q to the 3i, dot dot dot. So product of this. And let's prove this. So a partition, just consider lambda is a partition of n. Let's assume that we take one partition of n. Then lambda is a decreasing sequence of integers summing to n. So this, for example, lambda equals 6, 4, 4, 3, 3, 3, 1, 1. This is a partition of 24. And here, the decreasing sequence, the order of these doesn't really matter because we always order them in decreasing order. So you can think of this as a multiset. You can consider lambda as a multiset, or so that means lambda equals, we have one, there are two ones, so there are two ones, I'm going to write that like this, and nothing, there's no 2, and 3, number of 3's is 3, like this, number of 4's is 2, number of 5's equals 0, number of 6 equals 1, so like this. Now everything is now 0. So this means, this notation, multiset notation means number of 1's equals 2, number of 2's equals 0, number of 3's equals 3, etc. So what really matters is the number of parts equal to I. So if the number of parts equal to I equals mi, then we can write lambda like 1 mi m1 to m2, etc. But what this means is that we can construct such a partition from the right hand side of this generating function. So here, so this infinite product, so here we can take any of these terms, but if there are mi parts equal to I, then in this product we're gonna select q to the, we're gonna select here, we're gonna select q to the mi times I if number of parts equal to I is mi. So this number really tells us the number of parts. And that's basically the proof of this generating function. This, in fact, so for example, in this partition lambda here, this lambda is obtained by the following. So here on the right hand side, 1 1 plus q plus, this is I equals 1 plus dot 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 1 plus q squared q 2 times 2. Oh, maybe it's too much. 2 times 3. Let me have one more. 3 times 3. And times 1 plus 2 to the 4. 2 times 4. So we have a bunch of these. 1 plus 2 to the 5th. To the 2 times 5th. And then we have infinite product like this. And this can be obtained, so here, by looking at this, just look at this, because there are two ones. Here we select, this is 1, 2 times 1, so we select this term in the first factor. And then there is nothing for 2, so we select the constant term, the second factor. And for this, there are 3 threes, so we select this. 3 threes. And 4 twos, so we select this term. Nothing for 5, so select this. 1 6, so select this. And then for this, we select always 1 1 1 1 1, so that gives us just 1. So this, we have many terms, but among them we have q 2 times 2 plus 0 for the second, 3 times 3, 2 times 4, 0, 1 times 6, and then 0 times 7, 0 times 8, dot dot dot. This term really corresponds to lambda. So each term in the expansion corresponds to exactly one partition, and the size is exactly, the power of q is exactly the size of lambda. So this is the proof of this generating function. Okay, this is the end of the video. Thanks for watching.